Hi, I'm Ruben from Singapore, and today we will be exploring the analog to digital conversion process as part of the Coursera Introduction to Music Production Week 2 assignment. Mm, Having an understanding of this process will actually give users the appreciation of the modern day recording. As you know, previous recordings are done using analog tape machines, and there's high cost involved. Now recording is very affordable. Anybody who is interested can actually have a go at it. So, basis of recording modern day studios is actually the analog to digital audio conversion process. Firstly, you need to understand what analog audio is. Basically, it's audio represented as sine waves, data represented as sine waves. Whereas for digital audio, it's represented as a series of binary code in square wave form. If you don't know what binary code is, it's okay. We'll be covering it later in this short presentation. The conversion of a sine wave to binary code is basically the analog to digital conversion process, or known also as sampling. Digital audio, what's so special about it, or what is so different about it as opposed to analog audio? Digital audio is represented as binary code. So basically a series of 1 and 0 data sets to represent uh, sound waves or compressions and rarefactions as we have gone through in week 1. And sampling rate basically represents the frequency range that we're actually mapping over into a binary code. So for example, 48 kilohertz sampling rate actually represents 48,000 analog audio data points every second that's read by the computer. Bit rate will actually represent the amplitude range. Amplitude range in this case, basically the larger the word length, the larger the amplitude range or dynamic range as we will represent it. Simple formula is the word length is basically 2 to the power of the bit rate. So if you have a 16-bit audio file, it's actually 2 to the 16-bit audio data points in terms of amplitude. So certain common sampling rates that we're looking at, which we'll encounter, is actually the 44.1 16-bit, the standard for CD audio, 44.1 thousand samples of audio per second recorded, basically, and the word length of to the power of 16 characters. Other sampling rates we normally encounter: 48 kilohertz, 24-bit, commonly used for video recordings, television broadcast as well. And of course, 96 kilohertz 24-bit, mostly used in high quality studio recordings. This is the recommended sampling rate that we are using. Personally, I've actually encountered 192 kilohertz 24-bit as well, uh, used in live sound. So far, mainly the digital series of consoles with a certain stage rack is able to hit the kind of sampling rates. Audio quality definitely is better, but to most untrained ear, they will not be able to differentiate the 96 kilohertz to the 192. Okay, there's this frequency known as the Nyquist frequency, basically defined as half the sampling rate of an audio processing system. This is important to us because in the instance of analog to digital conversion, this represents the number of analog samples actually reflected within the sampling rate. So for example, you have a 44.1 kilohertz sample, actually reflects 22,000 analog audio instances instead of actually representing 44,000 audio instances. One thing to note is that this 22,000 actually also represents the maximum frequency that the audio sample, the digital audio sample, will actually hold. As you can see in the next point here. Okay, simple guidelines for analog to digital recordings as part of the analog digital conversion process. Okay, we know that we have to record at highest sampling rate possible. Okay, given the processing of the computer. Basically, what this does is that it gives you more leeway. Okay, when you are doing post processing, because you already have a larger sample headroom to play with. Recording at 44.1 versus 48 versus 96. At 96, basically, you're recording more audio samples, you're sampling more data points. So, having more data points gives you more leeway to edit. And one thing to note about sampling rates is that if any of your data points are actually edited, okay, or shifted, you can actually, it's actually fairly audible. So we got to take note to record at higher sampling rate possible, so that if need be, we can do any form of tweaks in instances where our recording has some kinks, or we have some digital clashes, digital noise from our source or from the laptop or the computer itself that we're recording from. Another thing to note is the setting of your sampling rate and your bit rate should be determined before the project itself, as change in the sampling rate will cause pitch changes, okay, in the recording. Basically, what happens is when you switch from 48,000 to 96,000 hertz sampling rate, we compress the number of uh, data points, okay, by half the time. Okay, for every second on a 96 kilohertz sample, we are supposed to have 96,000 points. If your original recording is only 48,000, essentially what we are doing is we are taking 2 seconds of that data and compressing it only into 1 second. So you basically have like a doubling of your pitch. The exception is, of course, when such velocity and pitch effects are actually desired as part of your recording, and that actually is the creative process that you have to determine beforehand as well. So, simple guideline, just remember, set a sampling rate, set a bit rate, such that your computer is able to record it without any distinct latency, and after that, you're good to go. And for this week's assignment, I've actually decided to explore the areas dealing with the basics of recording, the theory behind the whole analog to digital process. I'm a live sound engineer, but I'm still not as comfortable with a DAW, so I'm still exploring the works of it. I hope to learn more from everyone in this course, and I hope that this material is straightforward and easy to understand. Do let me know otherwise, and I will do better for following assignments. And I thank you for reading through the presentation.